We weren't. I mean, we weren't the best chemists in the room. I went in and showed them a pairing I'd done, and Jerry Donahue, he was a chemist. He said, it's wrong. You got the hydrogen atoms are in the wrong place. I just put them down like they were in the books. He said they were wrong. So the next day, you know, after I thought, well, he might be right, so I changed the locations, and then we found the base pairing, and Francis immediately said the chains run in opposite directions, and we knew we were right. So it was a pretty, you know, it all happened in about 2 hours. You know, from nothing to big. And we knew it was big because, you know, if you just put A next to T and G next to C, you have a copying mechanism. So we saw how genetic information is carried. It's the order of the 4 bases, so in a sense it is a sort of digital type information. And you copy it by going from strand separating. So it's, you know, if it didn't work this way, you know, you might as well believe it because you didn't have any other scheme. But that's not the way most scientists think. Most scientists are really rather dull. They say we won't think about it until we know it's right. But, you know, we thought it was at least 95% right or 99% right, so think about it. The next 5 years, there were essentially something like 5 references to our work in Nature. None. And so we were left by ourselves and trying to do the last part of the trio. What does the genetic information do? And it was pretty obvious that it provided the information to an RNA molecule, and then how do you go from RNA to protein? For about 3 years, I tried to solve the structure of RNA. It didn't yield, didn't give good X-ray photographs. I was largely unhappy. A girl didn't marry me. It was really, you know, sort of a shitty time. So there's a picture of Francis and I before I met the girl, so I'm still looking happy. But there is what we did when we didn't know where to go forward. We formed a club. And called it the RNA Tie Club. George Gamow, the great physicist, he designed the tie. He was one of the members, and the question was, how do you go from a 4-letter code to the 20-letter code of proteins? Feynman was a member, and Teller, and friends of Gamow. But that's the only photo. No, we were only photographed twice, and in both occasions, you know, one of us was missing the tie. There's Francis up on the upper right, and Alex Rich, the MD turned crystallographer, is next to me. This was taken in Cambridge in September of 1955. And I'm smiling, sort of forced, I think, because the girl, boy, she is gone. And so I didn't really get happy until 1960, because then we found out basically, you know, that there are 3 forms of RNA, and we knew basically DNA provides the information, RNA provides the information, protein, and that led Marshall Nierenberg, you know, to take RNA, synthetic RNA, put it in a system making protein. He made phenylalanine, poly-U made phenylalanine. So that's the first cracking of the genetic code, and it was all over by 1966. So that's what Chris wanted me to do. It was so what happened since then? Well, at that time, I should go back. When we found the structure of DNA, in my first talk at Cold Spring Harbor, the physicist Leo Szilard, he looked at me and said, "Are you going to patent this?" But he knew patent law and knew we couldn't patent it because there was no use for it. And so DNA didn't become a useful molecule, and the lawyers didn't enter into the equation until 1973, 20 years later, when Boyer and Cohen at in San Francisco and Stanford came up with their method of recombinant DNA, and Stanford patented it and made a lot of money. That is, they patented something which, could do useful things, and then they learned how to read the letters of the code, and boom, we've had a biotech industry, and but we're still a long ways from answering a question which sort of dominated my childhood, which is how do you nature nurture? And so I'll go on. I'm already out of time, but this is Michael Wigler, a very, very clever mathematician turned physicist, and he developed a technique which essentially will let us look at sample DNA at eventually 1 million spots along it. There's a chip there, a conventional one, then there's one made by photolithography by a company in Madison called Nimblegen, which is way ahead of Affymetrix, and we use their technique. And what you can do is sort of compare DNA of normal, say, versus cancer, and you can see on the top that cancers which are bad show insertions or deletions. So the DNA is really badly mucked up, whereas if you have a chance of surviving, the DNA isn't so mucked up. So we think that this will eventually lead to what we call DNA biopsies. Before you get treated for cancer, you should really look at this technique and get a feeling of the face of the enemy. It's only a partial look, but I think it's going to be very, very useful. So we started with breast cancer because there's lots of money for it, no government money. And now I have a sort of vested interest. I want to do it for prostate cancer. So, you aren't treated if, it's not dangerous. And but Wigler, besides looking at cancer cells, looked at normal cells and made a really sort of surprising observation, which is all of us have about 10 places in our genome where we've lost a gene or gained another one. So we're sort of all imperfect. And the question is, well, if we're around here, these losses or gains might not be too bad. But if these deletions or amplifications occurred in the wrong gene, maybe you really are sick. So the first disease he looked at was autism. And the reason that we looked at autism was we had the money to do it. To look at an individual was about $3,000, and the parent of a child with Asperger's disease, the high intelligence autism, had sent his thing to a conventional company. They didn't do it, couldn't do it by conventional genetics, but just scanning it, we began to find genes for autism, and you can see here, there are a lot of them. So a lot of autistic kids are autistic because they just lost a big piece of DNA. I mean, big piece at the molecular level. We saw one autistic kid, 5 million bases just missing from one of his chromosomes. We haven't yet looked at the parents, but the parents probably don't have that loss or they wouldn't be parents. Now, so our autism study is just beginning. We got $3 million. I think it'll cost at least 10 to 20 before you'd be in a position to help parents who've had an autistic child or think they may have an autistic child, and can we spot the difference. So this same technique should probably look at all. It's a wonderful way to find genes. And so I'll conclude by saying we've looked at 20 people with schizophrenia. And we thought we probably had to look at several hundred before we got a picture. But as you can see there, 7 out of 20 had a change which was very high. And in the controls, there were 3. So what's the meaning of the controls? Were they crazy also and we didn't know it, or, were they normal? I would guess they're normal. And what we think in schizophrenia is there are genes that predispose you. And whether this is one predisposes, and then there's only a subsegment of the population that's capable of being schizophrenic. Now, we don't have really any evidence of it, but I say, to give a hypothesis, the best guess is that if you're left-handed, you're prone to schizophrenia. 30% of schizophrenic people are left-handed, and schizophrenia has a very funny genetics, which means 60% of the people are genetically left-handed, but only half of it show it. I don't have the time to say it. Now, some people who think they're right-handed are genetically left-handed. Okay, I'm just saying that if you think, oh, I don't carry a left-handed gene, so therefore my children won't be at risk of schizophrenia, you might. Okay. So it's, to me, an extraordinarily exciting time. We ought to be able to find the gene for bipolar, there's a relationship, and if I had enough money, we'd find them all this year. Thank you.